Modern optical atomic clocks have reached a level of precision that allows us to slice a single second into 18 decimal places. By tracking the high-frequency quantum transitions of atoms like strontium, these devices can detect shifts in time that were previously invisible to science. This measurement is so sensitive that if you lift one of these clocks just a few centimeters off a table, it will record time moving at a slightly faster rate. The slight decrease in Earth's gravitational pull over that tiny distance physically alters the rhythm of the clock's ticking. Yet, while we can now measure a second with more accuracy than any other quantity in nature, we are left with a massive conceptual gap. After decades of refining the definition of a second, the physics community cannot agree on what these clocks are actually measuring. Human experience suggests that time is a universal flowing river, a steady movement from the past through the present and toward the future. It feels like the background container for every event in our lives, but the deeper we look into the mathematical laws that govern the cosmos, the more that familiar flowing river disappears. For more than 2 centuries, physics was built on Isaac Newton's description of absolute time. In his view, time was an independent cosmic clock that ticked at the same rate everywhere in the universe, regardless of the motion of planets or the position of an observer. This matched our daily perspective. It treated the universe as a rigid stage where events happened in a fixed, objective order that everyone could agree on. To explain why this stage feels like it only moves forward, we have to look at the behavior of matter. When gas molecules are concentrated in one corner of a box, they will naturally spread out until they are evenly mixed. This irreversible trend toward disorder is known as entropy. This statistical shift is why a dropped glass breaks but never reassembles, and why our brains hold records of the past but none of the future. It creates the thermodynamic arrow, the direction that gives our lives a sense of before and after. Classical physics described a universe that was easy to grasp, an absolute, unmoving stage governed by a clear one-way progression of cause and effect. That certainty was lost with Albert Einstein. By discovering that the speed of light is the same for every observer, Einstein realized that if light speed couldn't change, then the duration of a second had to be flexible. This effect is called time dilation. As an object moves at high speeds or sinks deeper into a field of gravity, its passage of time physically slows down compared to a stationary observer. This means that 2 different people can look at the same 2 events and correctly calculate 2 different sequences of when they happened. Because time is tied to your motion, there is no single objective now that applies to the entire universe. If 2 observers can disagree on the present, then the idea of a universal now loses its physical meaning. This led to the block universe theory, the idea that space and time are fused together into a single 4-dimensional geometry. In this model, the past, present, and future are all equally real and exist simultaneously within the space-time block. The events of your childhood and the events of your distant future are simply located at different coordinates on a static map. In relativity, time does not flow, it is a fixed dimension. This freezes the human experience of becoming into a massive, unchanging structure. But even the block universe fails to provide a complete picture. The current struggle in physics is trying to reconcile relativity's curved spacetime with the laws of quantum mechanics, which usually require an external ticking clock to function. When physicists try to merge these 2 theories into a framework of quantum gravity, the equations often refuse to work. This problem appears clearly in the Wheeler-DeWitt equation, which attempts to describe the quantum state of the entire universe. Since there is no observer or clock standing outside the universe, the variable of time vanishes from the math entirely. This suggests that at its most basic level, reality might be a series of timeless static configurations. We see change only because some of these arrangements contain records and memories of others. At the very base of the universe, it appears that time is simply not an ingredient. If time is missing from our deepest equations, we have to ask why it dominates every second of our lives. The answer might be emergence. Consider a single water molecule. It isn't wet on its own. Wetness is a property that appears only when you pull back and look at how billions of molecules interact as a liquid. Time could be a similar macro-scale property. A single quantum state has no temporal flow, But when billions of particles interact and create entropy, the sensation of time emerges. Physicists are still debating this. While some argue that time must be a basic, fundamental fact of nature, others see it as a byproduct of complexity. But this disagreement does not make our experience any less real. Even if time is an emergent pattern built from entropy and memory, it is the only way we can interact with the world. The present moment remains the only place in the cosmos where life is actually lived.